Dear participants, welcome to the Congress. Is my voice clear?
Yes, doctor, your voice is clear.
Okay, thank you. We can start. Dear participants, welcome to 5th International Congress on Human-Computer Interaction, Optimization, and Robotic Applications. We are in session 2.2 now. We have 8 papers that will be presented in the session. Each participant will have 10 minutes to present their works. So the first paper, the title of the first paper is High Performance FIR and IIR Filters based on FPGA for 16 Hz signal processing. And I guess Yusuf Samer will present. If you are ready, you can share your screen and start your presentation.
Okay, doctor. Doctor, before I start, I just want to tell you that my presentation maybe will take the 12 minutes maximum. Will that be okay to cover up all the topics that I have?
Okay, but try to summarize in 10 minutes, but that's okay.
Okay, I'll try my best. Okay.
Okay, you can start.
Greetings, my name is Yusuf Mudaffar. I'm a lecturer in the Islamic University in Iraq. Our work is titled High Performance FIR and IIR Filter based on FPGA for 16 Hz signal processing. For the contents, we will go through the problem and solution, aim of project, and the application. We will go through a brief explanation about digital filter, then on the FPGA. After that, designing and simulation of the digital filter will be covered. Then the result will be shown and discussed. And finally, we will go through the conclusion and future work. The primary issue with this study is that the majority of hardware devices filter are unable to handle signal with extremely low frequencies, such as ECG signal. As a result, there is a lack of consistency between the simulation and practical implementation of digital filter. However, by utilizing FPGA, which is capable of processing extremely low frequencies, it becomes possible to achieve identical outcome between the simulation and practical design of digital filters. The objective of this project is to create a range of FIR and IIR digital filter and deploy them on FPGA, leveraging the numerous benefits that an FPGA provides, such as speed, accuracy, power consumption, processing time, and of course, parallel processing capabilities. This filter can be applied to a wide range of applications, include signal filtering for ELF and noise cancellation purposes. Digital filter is a mechanism that utilizes mathematical operation on a discretely sampled signal in order to modify specific characteristics of the signal. This differs from an analog filter, which functions with a continuous time analog signal through electronic circuits. So digital filter has many advantages over analog filter, like they are less sensitive to environmental changes and provide more flexibility, and it is programmable, and it is easy to simulate and design. Basically, we have 2 types of digital filter: finite impulse response and infinite impulse response. First, let's talk about the FIR filter. The filter responds to 0 after the impulse passes through the system. Its impulse response stays for a finite time. As we can see from the figure, samples enter the filter, it will be multiplied by a weight and then added to the second order after multiplying it with the second weight, and so on, depending on the order of the filter. 3 methods for calculation of FIR filter coefficients there is. First will be window and optimal and frequency sampling. Our focus here is on the window method for its simplicity. FIR faces the issue of spectral leakage when measuring signal with non-integer periods, lead to sharp transition. Windowing can minimize this effect. Basically, we have 4 types of windowing. Rectangular is the default one, Han and Ham, and Kaiser. Rectangular window has a value of 1 in a specific interval and 0 elsewhere. Han and Ham window are sinusoidal with wide peak and low side loops. Han window eliminates discontinuities at both ends. But for Kaiser window, it has a balance. It has a balance between the type that we mentioned before. For the infinite impulse response filter, never quite reaches zero due to the presence of feedback. Its response stays for an infinite time. Time taken is much larger than FIR. The feedback of the IIR filter can be shown in this figure. There are two sets of filter coefficients. The coefficient A is called the feed forward, and the second one is called the feedback. For the type of IIR filter, we have four types: Chebyshev 1, Chebyshev 2, elliptic, and Butterworth. For the signal response on low-pass filter of Butterworth, it has a smooth transition. It has no ripple, but it is the slowest compared to the rest. For Chebyshev 1, it has a ripple on the stop band, and it is sharper and faster than Butterworth. Chebyshev 2, it has a ripple on the pass band, and the rest is the same as the previous one. And lastly, for elliptic, it has the fastest execution speed and sharpest transition, but has ripple in both pass band and stop band. So FPGA basically is a reprogrammable device for customer configuration. It performs any digital function using logic gates like AND and XOR. FPGA have configurable logic block connected by programmable interconnect. They run multiple tasks simultaneously with no delay, relying on hardware instead of software. In our work, we chose the Spartan 3E series due to its advanced low-cost feature, and it meets the requirements of our work. Here are the filter design and analysis tool, where the filter was designed by entering the specification like frequency, response time, design method, and filter order. We can get the coefficients of the filter from this MATLAB tool. Basically, it's a tool that can be found in MATLAB. Here are the specifications that were used to design the filter. We used the low pass signal and an input signal of 16 Hertz, very low frequency to make it very close to an ECG signal. The signal type was a sine with a 2-volt peak-to-peak and a sampling frequency of 1000 Hertz. Here's the block diagram of the filtering processes. The input was a signal from MATLAB, will be sent through the JTAG programmer, which is connected to the FPGA, and from it to the FPGA, where it gets filtered. Then it will be sent back to the JTAG, and from it to MATLAB and the personal computer, and shows the result of the filtering in it as an output. Here's the simulation circuit of the FIR low-pass filter with Kaiser window of the 5th order. Basically, what we did in this work, we created FIR circuits with 4 types that were mentioned before. Each one have 3 circuit order, 5th, 8th, and 10th order. But in this presentation, only the best resulting filter were shown. We added a sine signal of 16 Hertz with a random noise and entered the simulation filter created in Simulink in MATLAB, and the results were compared to the filtering results, which were uploaded to the FPGA, and then we compare the result of the FPGA and simulation. Here's the same FIR filter, but with the 10th order, and that would make the filtering result much more accurate. The same happened here as the previous circuit, but will be more accurate. As we can see, the frequency response of the 10th order are much more accurate than the 5th order. The cutoff frequency of the low-pass filter is 16. So the higher the order, the more accurate the result will be. Here are the simulation circuits of the IIR of type Chebyshev 2 of the 5th order, which has a feed forward and a feedback. And the rest will be the same as FIR. We input a sine signal of 16 Hertz with added noise and filtered them through the simulation, which gives the optimal result, and see the difference between it and the same practical circuit uploaded to the FPGA. Here it's much more complex and long circuit of Chebyshev 2 because it has a 10th order. It also has a feed forward, feed back, and of course will be better than 8th and 5th order. The frequency response gives a good result since it has a sharp transition from 16 Hertz, and the magnitude will be much less after the cutoff frequency compared to the FIR result we got. By comparison, IIR filters are faster with higher efficiency, but it can be unstable compared to FIR, and it is more complex. For the results of FIR low-pass filter Kaiser window of the 10th order, first we see the sine signal, then the then the signal with added noise to see the filter efficiency. The simulation result gives the filtering result that removes the noise from the sine signal, and the practical result shows the filtering signal from the FPGA. by using the same filter used in the simulation. We can notice that if we subtract the simulation result from the practical result, it gives 0, which shows that the FPGA gets an optimal and high accuracy filtering result for the low frequency signal. Here are the difference between the original sine signal and the filtered signal after removing the noise. It shows the difference is very small. By using IIR filter with Chebyshev of 10th order, we also get a filtering result, which are very good. We can see the sine signal, then the sine signal with noise. After that, the simulation result and the practical result in the same figure. Okay, so the same here happens when we subtract the simulation result from the practical result. It also gives out 0, which means the results are identical. For the efficiency of the filter, it can be shown it has much better filtering result from FIR filter, nearly 0, except for the beginning of the filtering result, since there will be always a small delay until the accurate result will be reached from the IIR filter. But the difference will only be in a short and unnoticeable time. The figure shows the FPGA connected to the JTAG and from it to the personal computer to communicate with the MATLAB. I'm sorry, I'm trying to make it as fast as possible. We can also see here the resources usage of FPGA when uploading the 2 previous FIR and II filter. We can notice the number of slices are much higher in usage for the IIR compared to FIR due to the presence of feedback in the infinite impulse response. For the conclusion, we can conclude that the best results of all the tested filters are the FIR Kaiser window filter of the 10th order, of course. And for the infinite impulse response, Chebyshev 2 was the best one of the 10th order. Basically, FPGA simplifies hardware building and ensure identical simulation and practical results. And FPGA enable filtering for extremely low frequencies like 16 Hz. And max filter order in our work for the infinite impulse response was 10th order. And for the finite impulse response, it was 20. Due to the FPGA multipliers limit, if we use another FPGA, we can make a more multiplier and more order, basically. Utilizing and for the suggestion for future work, we can use another FPGA Spartan series to increase the filter order capability. And we can explore a new input signal like ECG and filter signal in the higher accuracy range, like in megahertz or gigahertz using FPGA. And we can also connect the FPGA to a DAC circuit for real-world filtering display instead of the work that we did, which is MATLAB Simulink hardware co-simulation. Thank you so much. I reached the end of my presentation.
Okay. Thank you very much for your presentation. Dear participants, do you have any questions about the presentation? Okay, I guess there are no questions. We are moving on with the next paper. The title of the paper is Signal Change Estimation of One Important Class in the Filtering Process. Are the authors here? Okay, we can see your screen, and if you are ready, you can start. But we can't see your voice. We can't hear you.
I am ready.
Okay,
One minute.
we can hear. Yes, we can hear you. You can start. You have 10 minutes to present your work. You can start. But we can't hear you. Okay, you can start.
The active development of society creates the need to consider and solve new problems and to give new interpretations of existing views. This is especially noticeable in technical field. Digital signal processing is one of the most relevant research areas. A number of problems of digital signal processing have already become classical, and therefore the theoretical and technical methods of their solution have been developed and adapted to modern realities. However, when these methods become methods of solving not a global problem, but its sub-problem, or are considered from a different perspective, a number of additional questions may arise regarding the specifics of solving the problem. This is especially strongly reflected in the technical aspects of the digital signal processing system. Signal filtering is known to be among the classical problems of digital signal processing that can be used only at certain stages of solving the given problem. In order to filter the signal described by the sum function x from t, it's considered in the frequency spectrum. To move into the frequency spectrum of the considered signal, we have to apply to it the Fourier transform 1. For the direct implementation of signal filtering, the weight function here is introduced, the function by which the integrand in 1 is multiplied and carried out. As a result, the Fourier transform is obtained by a second function, where y delta from t is a result new signal. In some aspects of technical implementation of the task, we have to study the change of the signal x from t due to filtering. In another words, the different two. One of the well-developed methods how to do this is to use corresponding signal transformation in previous slide, what in replacing in the of equality 2 gives second formula. The main goal of this work is to consider the general statements about the behavior of the difference 2 for signal from the class W R alpha, where R is equal or more than 0. In particular, we will study forms 3 and 4. To demonstrate the use of these estimates, the measure of the signal change when filtering with a filter has been investigated for filter 5. Let the function x from t belong to the class of function W R alpha that has a summation Fourier series 6. We will consider the function tau that can be denoted similarly to some works and introduced a lemma that is valid for this function. This lemma we may see on this slide. Let us now assume that the function tau satisfies the conditions of this lemma and the function x is from WR alpha, has the Fourier series. They will consider the next integral, what we can see in the first formula. Since t from L and some function f r alpha is a bounded periodic function using Parseval equality and the introduced lemma, we can obtain the following equality 10. To obtain the polynomial y delta for function x from t, we assume that the function tau from 10 at u equals k divided by n is given the first equality. That is, as a function tau, we should take the function lambda n. Thus, we have equality 11. Representation of the deviation 2 for function x from the sum 11, assuming that for u equals k divided by n, the function tau is given by quantities of the form in the next function. As a result, we have formula 12. For those function tau which are from tau less than infinity, we introduce notation 13.
Dear participants, you have 2 minutes left. Please try to sum up.
Theorem 1. What describes an estimation of signal change from class WR alpha? Let's prove this theorem. From 10 and thank you.
Oh, okay, thank you for your presentations. Are there any questions about the presentation? I guess there are no questions. We are moving on with the next paper. The title of the paper is Cellular Automata Aspects and DNA Coding-Based SPM for Image Encryption. I guess Omar Omran will present. Are you ready? We can't hear you. Check your microphone, please. We can't hear you.
Hello.
Yes, we can hear now. You can start.
Okay,
You have
everyone.
10 minutes.
Hello, everyone. I'm Omar Omran, and today I'm going to present the paper I wrote with Dr. Wasim Alexan, titled as Cellular Automata S-Box and DNA Coding-Based SPN for Image Encryption. This is the outline that I will be following today: introduction, the proposed scheme, performance evaluation results, conclusions, and future work. Starting off, we need to do image encryption, as sharing images over the internet, which is an unsecure channel, is an everyday thing that everybody does. Thus, we need to encrypt the data or the images sent over the internet. And our crypto system is composed of 3 stages. Starting off by the cellular automata. Cellular automata is an automaton is a self-operating machine, and cellular automata was introduced by Stephen Wolfram in 1983. Cellular automata can be defined mathematically by this equation, and it can also be defined graphically by this graph that you see in front of you. Actually, this graph is generated depending on the 8 rules presented above. It starts off by plotting a single pixel in the middle of the grid, and then it keeps on moving and it checks, and then it follows those exact rules, and then it colors those pixels depending on those rules. For example, here we have this pixel, and then if we go this way, so white, and black should give a black pixel underneath, and then white, black, and white should give also a black pixel underneath. So it keeps on going. You can generate as much as lines as you want. So here we have 15 steps, which you can see in front of you. Why this is interesting, or why we use this, because it seems chaotic, it seems vague. However, it's not. It is defined by a rule. And what we actually do is, after we generate X number of steps, we take the middle column of this grid, and then we transform it into a bit stream. For example, here you can see this bit stream is 001, as written here, as long as we want to be the key for our first encryption stage, which is the image is transformed into a bit stream, and then with the resulting bit stream of this one, it is XORed with the bit stream of the image, and then it gets back, it gets out the first encrypted image. For the second stage, we utilize a substitution box, or an S box, and the S box basically what it does is it goes through the image pixels, and then for the first pixel, it tells the pixel in this position to go to position number 121, and then it keeps on going. For each pixel, it just substitutes its place with the number written inside the S box. And then you have a shuffled image, which was already encrypted in the first with the first stage by cellular automata. Following by the third stage, which is based on DNA encoding. This is the image of the DNA strand. We are not really interested about the chemical composition of the DNA. However, what we are interested about is the basic chemical components of the DNA, which are defined by A, G, C, and T. What we actually do is that we assign each 2 bits, we assign them to a certain letter from the A, G, C, and T. And there are 8 rules to follow if you would like to do such thing. You can either follow the first, second, third, or even the 8th rule. For each 2 bits, you can assign them as A or as T, and you can do that upon your preset. And this bit stream is generated by a pseudo-randomly generated number, which is called the Mersenne twister. And after this bit stream is generated, you just turn or assign the bit stream, like if you have 0, 0 followed together, you assign it to whether A or one of the rules. And also you change the, you convert the image that you have taken out from the S box. You also convert it to a binary bit stream, and then you convert it to DNA. And then you have the operations that you can perform using the DNA, which in our case, we are using the addition and the subtraction. So those are basically the set of rules that define how you can add or subtract 2 DNA strings from each other. Okay, so this is the flow chart of the crypto system that we are proposing. First of all, you have a plain image. You convert the plain image into a 1D bit stream. At the same time, you generate the cellular automata with rule 30 specifically. And then this is a bit stream. You shuffle the bit stream, and then you XOR the bit stream with the plain images bit stream. And then you end up with the first stage, or the first bit stream of the image, which is encrypted. And then you reshape the bit stream into an image, and then you apply the S box on the image. The S box is applied on the image, not on a bit stream. And then you're left with the second stage encryption for the image, which is a fuzzy image. I will show you later the following slides. And then you convert the S box image into a 1D bit stream, and then you convert this 1 bit stream to DNA upon the rules I showed you earlier. At the same time, you generate a Mersenne twister bit stream. Mersenne twister is pseudo-randomly generated number. And then you convert this bit stream to DNA, and then you add both strings, which are made up of DNAs. After that, you reshape the image, and then you finally have an encrypted image made up of 3 stages. This chart here, it shows the inverse of what we just did, which is the decryption. You have an encrypted image, you convert the image into 1D bit stream, you convert it to DNA, and then at the same time, you also generate the Mersenne twister bit stream, you convert it to DNA, and then this time you subtract both DNA strings from each other, and then you convert the image or the DNA you have to a 1D bit stream, and then you reshape it to an image, and then you apply again the S box, which you've applied already in the encryption scheme. You apply it once again, and then you're left with a fuzzy image, which is only left, which you need to only decrypt once more to reach the plain image, which you already had. You generate the with 30 serial automata bit stream, you shuffle it, and then you XOR it with the bit stream of the image, and then you're left with the plain image.
Mr. Roman, your time is finished. Please try to conclude and summarize.
Okay, so those are the performance evaluation results. This is the visual and histogram analysis. This is the image. This is the encrypted image. This is the histogram of the plain image. This is the histogram of the encrypted image. And those are the numerical results for the House, Lena, and Mandrill image. And those are the numerical results compared to the literature. In conclusion, we discussed the proposed image crypto system and the performance evaluation results. And for future work, we could look into using other cellular automata rules. Those are the references. And thank you so much.
Okay. Thank you very much for your presentation. Dear participants, do you have any questions about the presentation? Okay, if there are no questions, we are moving on with the next paper. The title of the paper is A Real-Time Smartphone App for Field Personalization of Hearing Enhancements by Adaptive Dynamic Range Optimization. I guess Nasser Kahtar Nawaz will present. Are you ready?
Hello, good morning. Can you hear me?
Yes, we can hear you. You can share your screen and start your presentation.
Can you see my slides?
Yes, we can see. You can start.
Okay. Hello, good morning, everyone. My name is Nasser Kahtanavaz. I am with the University of Texas at Dallas in the US. This work has been done by one of my PhD students as part of his dissertation work, Austin Nee. And what I'm going to talk about is coming up with a smartphone app in order to personalize hearing enhancement by this prescription, which is called Adaptive Dynamic Range Optimization. ADRO is an amplification strategy that is used for hearing aids, hearing assistive devices. In our previous works, we've shown that if we personalize this prescription, this amplification strategy, we would get better outcome, hearing preferences by users. We've reported those findings in the references that you see on this slide. This particular work is about making that personalization feasible in the field, in real-world audio environments. Here is an overview of ADRO. We compute percentile of sound pressure levels, and we have a number of parameters like loudness, discomfort level, comfort target, and auditability target. So all these parameters are used to make adjustment to gains in a number of frequency bands. The curves you see here basically indicates how ADRO works. We have the upper curve indicate the comfort target, the lower curve, the audiogram of a user, and the two curves in between, basically those are percentiles of sound pressure level, high and low. And we want, the idea here is to put those two sound pressure levels between the lowest hearing level, which is audiogram, and the comfort target level. So it's by moving these lines up and down, by making adjustment to the gains in different number of frequency bands. The way we did the personalization by we use maximum likelihood inverse reinforcement learning. And the idea here is basically to find an optimum reward function based on hearing preferences. We are using basically a Markov decision process to do this. States and actions in this Markov decision process consist of comfort target levels across a number of frequency bands. Based on preferences that the user provides, there is a human feedback here. We set up this likelihood function and then find the reward function in such a way that likelihood function is maximized. The details of this personalization again is discussed in this paper indicated on this slide. So we've already done subject testing. What you see here is the audiogram of 10 subjects, a standard ADRO comfort target, and personalized ADRO comfort target. These are gains in dB in different frequency bands. And we've shown that the personalized approach by far is preferred over the standard approach. The bar chart you see is the percentage of cases that subjects preferred over a standard ADRO amplification strategy. And we also looked at whether this approach, had any the adverse impact on word recognition, and the chart on the right indicates that there was no adverse impact on word recognition. Now, in this work, we took that personalization algorithm and made a smartphone app out of it. What you see here is the entire pipeline of the app. We bring down first, in order to have the lowest latency on any smartphone, we need to do the sampling at 48 kilohertz. That's governed by the I/O of smartphones. But if we do the sampling at 48 kilohertz, we won't have enough bandwidth to do our processing. So we bring the sampling rate down to 16 kilohertz, do our processing, and then take the sampling rate back up again. Here in this place, we are applying the ADRO. That's where the adjustment in gains are done. And then the algorithm MLIRL is doing the personalization on the right-hand side. Here are the attributes of the smartphone app for both iOS and Android. Basically, we can do these frames in less than 1 millisecond, which means that no frames get escaped. We can achieve real-time performance. And the CPU utilization, the memory size that is used by this app are also indicated on this slide. So the whole idea here is basically to take the necessary steps, which is governed by the hardware of smartphones, in order to make that personalized app work in the field, in an actual real-world audio environment. This is the app GUI. There are two components to it, a training part, a testing part. In the training part, we do a paired comparison between different comfort. We go through a number of iterations, about 20-25 iterations, and that creates the personalized setting. And then we switch to the operation mode or testing mode, where we can study the difference between the standard prescription and personalized prescription. Here are some results in different real-world audio environments that were conducted by the smartphone. And so in different types of environment, music, speech, different types of background noise, babble, machinery, different types of noise. And you see the different comfort targets that are generated as a result of the personalization. Let me show you a couple of sample audio here. This is what we hear from standard audio standard ADRO.
Imagine will feel worried, threatened, and at risk. But there is good news. The quality of care that children receive in their families can have a more significant effect on their well-being.
And it keeps getting advanced. This is the personalized version of it.
That they have been exposed to. So actually, children can be protected by warm, secure parenting during and after conflict.
One more example.
Who have, because of the disclosures, moved away from our ability to have insight into what they're doing. The net effect of that is that our people who are overseas in dangerous places, whether they're diplomats or military, and our allies who are in similar situations.
And there is also a video clip. I don't know the video clip is going to show. I'll try to see whether
You have 1 minute left. Please try to conclude. Did you finish your presentation? We can't hear you. We can't hear you, Mr. Keter Navas. Are you finished? Okay, if you are finished, thank you. We can go on with the next paper. The title of the paper is Wireless Body Area Networks Application and Congestion Control Technologies. Our daughters here. Okay, we can see your screen, but we can't hear you.
Hi, everyone.
Okay, we can hear. You can start.
Hi, everyone. I am Ahmed Shakir. I will present Wireless Body Area Networks Application and Congestion Control Technologies from University of Anbar. What is the Wireless Body Area Network? Wireless Body Area Networks is the wireless network of wearable computing devices. The body area network field is allow inexpensive and continuous health monitoring with a real-time updates of the medical records through the internet. It is a special purpose sensors network designed to operate autonomously to connect various medical sensors and appliances located inside or outside of the human body. The position wireless body area network, the protocols developed for the wireless body area network can span from the communication between the sensors on the body to communication from the a body node to the data center connected to the internet. Thus, the communication and the wireless body divided into parts: the intra-body communication and the extra-body communication. And the intra-body communication, the terms of the intra communication is used for the ratio communication inside the wireless body area network among the body sensors inside the body, and the communicating between the wireless body area network and the tier 2. It will be around 2 meters in or the about the human body. The body sensors are the accountable to gather the vital data from the body and then forwarded to the personal surface. The personal surface can be incorporated on the PDA or the cell phone or the home PC. The main objective of the personal LPS is to forward the vital information to the medical server over the network, while the extra body communication ensure the communication between the personal devices and the extra network. Here in the architecture of the wireless body area network, as the medical service develops, the hospital are now available to remotely gather the patient information from bedside the monitoring devices. The remote gathering and the investigation of the medical information has given several chances from the clinic and the researcher. And the information gathered from the patient supply the capability to extrapolate the observation depend on the crowded and the historical information. The wireless body is becoming the promising the technology in the field of the widely and remote health monitoring. The wireless body network has the ability to gather the patient vital information in addition to create the communication link to gather the data medical center. Also, it is suitable resources management of the huge amount of the monitoring information is the critical issue in remote electronic healthcare system. Also, there is some restraint related to wireless body area network. For example, the limited memory, power supply, and the communication capabilities. It is also, as we know, the architecture wireless body area network is classified for 3 tiers: the tier 1 and tier 2 and tier 3. Tier 1 is consists from intelligent nodes, including the sensors, the medical sensor device to measure the ECG, EMG, SpO2, and blood pressure signals. Also, the minimal input text a patient usually attends the collection completing to the VisiClient by manually completing from form that characterize the pathological cases. The image, also many images by the users can capture it and forward it to the doctor for the pathological cases estimate. While the entire to the personal server is responsible for interface for the wireless body network sensor nodes through the ZigBee or Bluetooth connected with the medical server through the mobile telephone or the 2G, 3G online internet. Implement also the cell phone. The functions register types on the number sensor node and manage the network channel sharing, time synchronization, and the processing data, send the data to the server. The tier 3, the functions is authenticate the users, save the patient details in the medical server, analyze the data, recognize the serious health cases in order to connect the emergency care gives, the forward new instructions to the user. The type of the patient can be handled, the patients who suffer from the chronic disease such as the diabetes, asthma, and the heart attack. Also, this network is placed on the patient can be alert the hospital even before they have a heart attack through the measuring the change in their vital signal. Also, on the wireless body area network on the diabetic patient can auto inject insulin through the pump as soon as their insulin level descends. The advantage doctor can follow the vital signs of their patient at the same time, can be alerted if one of them has got a problem. Emergency services can be get from a doctor. Patient has not required to physical available to the doctor. The problem description here, in order to deal with the congestion problem in health, the server application, it need emphasis on many-to-one communication model. Many-to-one communication is indicated to the connection when some sensors node send data to the signal sink at the same time. Type of the congestion, we have two types of the congestion, node level congestion and link level congestion. And the node level congestion, it can be occurred because of the buffer flow in the specific node. While the link level congestion is indicate the congestion when a wireless channel are the common by the more and few nodes in the same sensor connect available channel. Similarly, congestion is a proper execute. Here in the congestion detection, this congestion control mechanisms, congestion control mechanisms are classified in two source-based or the network-based method. The source-based algorithm are circulating at the end host where the transporting protocols are compatible to detect the congestion. The network-based algorithm, on the other hand, is implemented at the intermediate node, especially the routers. The congestion control mechanisms is classified by the three types: the congestion detection, and then congestion notification, then rate adjustment. And the congestion detection unit method is an important part designed occurs for efficient congestion management protocol. There is two types for the congestion detection: a local congestion detection and global congestion detection. And the local congestion detection is performed in the at the intermediate node by considering node features such as the buffer capacity and the congestion index, while the global is performed around the sink node. So in the congestion detection in early stage will be at the local detection method preferred over the global types. While on the rate adjustment unit, the main objective of the rate adjustment unit to adjust the traffic rate of the upstream the nodes. And the healthcare application, well, we are dealing with the human physiological science. The main objective to give priority for the traffic. For example, the some vital priority, the high rate, the signal is high priority than the other, such as the temperature. So in case of the high traffic load, it's necessary to transmit most important information first. While the congestion notification is given notify, we have two types: the X-place congestion and M-place congestion detection. And the X-place, the congestion node is use the special control message to notify about the congestion. As a result, method will be increase the network overhead. While on the M-place, will be sent with the necessary with the header of the data buckets to avoid the heavy traffic migration. Here we have a different type of the preposed congestion control method by the other orders. For example, they suggest different congestion detection method and rate adjustment and congestion notification. For example, the PCCP, they suggest the congestion detection based on the arrival time and the bucket surface time, and the rate hop by hop and in place. The quality of service evaluation, the bucket loss and rate and the delay. And thank you very much.
Okay, thank you very much for your presentation. Dear participants, do you have any questions about the presentation? Okay, if there are no questions, we are moving on with the next paper. The title of the paper is Properties of Low Frequency Filters of One-Dimensional Signals with Limited Energy Spectrum. Are the authors here?
Yes. Good day, colleague. Unfortunately, we don't have much good news. Fascist Russian does not give the opportunity to work. The connection may be interrupted. Perhaps there will the rocket fire of Iran drone, and you will have to hide. But we are indomitable, and we are working. Yes.
Properties of low frequency filters. Okay, you can start.
Hi everyone, my name is Andrei Makarchuk, and I will tell you about properties of low-frequency filters of one-dimensional signals with limited energy spectrum. The choice of a weight function to solve a given problem requires a sustained understanding of the specifics of studying problem. Nevertheless, the use of the weight functions has found a fairly wide application in the number of theoretical and applied research areas. In particular, weight functions are widely used in digital signal processing to solve the problems of filtering and smoothing studied signals. One of the rather important problems that can be solved with the help of weight functions is the problem of suppressing low or high frequencies. Moreover, the use of weight functions as a method of frequency suppression is quite universal. The purpose of this work is to demonstrate that weight functions are applicable to both Fourier series and Fourier transformations. Therefore, the weight functions should be studied from various angles, increasing both theoretical and practical interest in them. In the first part of this work, two statements about low-pass filters applicable to signal from the class L2, in the case where the Fourier series is used to represent the signal in the frequency spectrum, have been considered. In the second part of the work, similar statements have been introduced for the weight functions in the case of using a continuous transformation. Using the same goal of their application has been demonstrated on a concrete example of a low-pass filter. Let V is some weight function given in the form of a triangular matrix with numbers where Vn0 equals 1 and Vn plus 1 n equals 0. For this matrix, we put first three equations for all k from 0 to n minus 1. For any 2p periodic function phi from x, what is integrable on the segment 0 to p with its Fourier series, we put some operator ln in formula 1. Now let's us show the following statement. If we have equality 2, then the sequence of linear operators ln at all at n go to infinity converges uniformly to the function phi from L to P. Then, using the method of some number of works, we may show the validity of the following lemma 1. What can be formulated in the next form? In order of sequence of linear operators Ln, uniform and x from 0 to p, for each function phi from C to P, it's necessary and sufficient that the following conditionals are fulfilled. First condition is limit of phi kn when n go to infinity equals 1, and that integral 2 will not more that some constant. And finally, the validity of the theorem 1 follows when we use a relation 3, 9, and lemma 1. Now let's see now we may verify the fulfillment of lemma 2. The second condition we may calculate analytically, but the first condition we may show if we build graphs of weight function for different omegas. And the result, we may see that lemma 2 is also true for weight function Vn. It is worth noting that theorem 2 and lemma 2 hold for many other widely used functions that can be used as low-pass filters. Such functions include the sigmoid function of the kind 14, modification of arctangent like 15, and many others. It turns out that the function for which theorem 2 and lemma 2 hold are more versatile in the context of use in digital signal processing than some other mentioned in some works. For example, this kind of functions can be used not only as low-pass filters or signal smoothing functions. With some modifications, they are suitable for solving other problems such as signal restoration. For example, functions 14 and 15 with algebraic transformation are transformed into functions that are classical activation functions in machine learning, the model of which are often used for various processing of digital signals, including their recovery. Conclusions. In the paper, we have considered two significant properties of low-pass filters for signals with limited energy. Their form has been demonstrated in the case of usage of Fourier series and in the case of usage of the Fourier transform of considered signals. These properties have been demonstrated on concrete examples. During the experiments, we have established that many widely used functions possess these properties. Their examples have been given. The versatility of solving the problems, such as recovery, has been also revealed. Thank you for attention.
Okay, thank you very much for your presentation. We are going on with the next paper. The title of the paper is Patch Antenna Design for Q-band Application. Are the authors here? Are the authors of the paper with the title Patch Antenna Design for Q-band Application here? Okay. I guess they are not here. We can go on with the last paper. The title of the paper is Detection of Clips Failure in Manufacturing Using Audio Signals. I think Sabri Suer will present. If you are ready, you can share your screen and start your presentation.
Okay, can you hear me?
Yes, we can hear you.
Wait a second. I hope you can see this.
Yes, we can see your screen and you can start.
Thank you very much. I am Sabri. I am a master's student in Istanbul Technical University and working in Threading Motion as a data researcher. First of all, I apologize for these first 3 slides are in Turkish. I was blindsided and didn't realize until the last second. I will summarize. Threading Motion was founded in 2017. From 2019 onward, the company started attracting investors who are listed below the slide. It is smart wearable company. Smart glove smart glove was produced, which is used to help employees in quality control tasks. I'm sorry. This is the previous slide. Many different types of gloves were manufactured. They have different uses and specifications, such as QR code scanner and different scan durations, etc. They are used automatically at demand, or our use case is about recording audio, detecting particular sound events, processing it on the device, and providing feedback immediately, which will help employees on assembly line. This shows how the smart glove is used in automotive sector. It can be used to find corresponding pieces during assembly, verify finished product during quality control, and so on. In manufacturing, there can be some processes where verifying whether it's completed correctly or not is difficult due to the lack of or minimal visual cues. Artificial intelligence can be used to verify these processes using audio data to lower human-based errors. Our use case in this scenario study was detection of clip sounds in automotive manufacturing. There is a connector on seat belt buckle that informs the car safety system whether the seat belt is fastened or not. If this connector is not plugged in correctly, the failure may be detected in the tests before shipping, which would cause the car to go back to the beginning of the assembly line. This would cost the manufacturer worker time and other resources. In the worst case scenario, it may fail after shipping and result in a car accident, which is very bad. This connector is small and difficult to inspect visually. When employees plug it in, it emits a particular sound that we will be calling clip sound. Our goal in this study is to detect these sound events. We utilize autoencoder autoencoders models and proposed our own architecture to tackle this problem. We collected data from a contracted car manufacturing factory to use in this project. This data come from the connectors of the rear seat pads. This connector is plugged in a cramped area. It is difficult for employees to make visual inspection during assembly. To collect data, a microphone is attached to an employee's hand and recorded the noise throughout the process at a sampling rate of 16 kilohertz. While the connectors are plugged in, another employee used a stopwatch to mark the timestamps that contain clips sound events. They are then used to annotate the audio data. Since audio was recorded throughout the assembly work, we also have a great amount of ordinary background noise of the factory. The table shows the amount of samples for different classes in seconds and number of samples of 0.4 seconds long. As we were collecting data, our data granularity increased. At first, we only annotated any connector which are denoted as undetermined. Then we started annotating 3 different clips coded by color. However, these fine grain labels weren't used in this paper. Everything was considered simply clip sounds. This is how our data looks like in both waveform and spectrogram form, which contains both time and frequency information. The clip sound sample can be seen between 4 and 5 and also just for 7. They also generate some amount of echo. The clip sound usually preceded by a noise made by placing of the buckle on the car frame and followed by a noise when the connector is stuck on top of a fabric to prevent it from moving freely. The clip sound is easy to observe in these samples as the gloves that the microphone attached to is in close proximity to the connector. In a noisy factory, employees have hard time hearing it. There's a sample here. I don't know if you will be able to hear it. I'm not sure if that was that to you. We focused on 3 types of features in this work. Most machine learning models don't use directly use audio data in waveform. Since frequency holds useful information, Fourier transform is used to extract them. It is applied to the signal window by window to extract frequency data, which is called a spectrogram. This process is called short-time Fourier transform, also STFT. A common approach is then to apply mass scale to this spectrogram. This scale mimics how humans perceive frequencies. It tries to equalize the distance between 2 frequency bands to be equal to how humans perceive them to be. It appears that humans have higher resolution for low frequency audio. So mass scale squishes the high frequency bands and lengthens the lower ones. The reason the mass spectrogram looks the way it is because most data points are small numbers, but there are many outliers which reduces false color variety. I used 99 quintile of the data to make it look somewhat better. On top of mass scale, we can convert the data to decibels, which we denote as logmel. This does reduce the effects of outliers, at least for visualization purposes. Finally, we have also tried mass frequency Kapstrom coefficients transformation, which is acquired by applying cosine transform on MEL features. As we have a few data samples, we wanted to utilize unsupervised methods. We can train an autoencoder where a model learns to construct the ordinary background noise of the factory. Later, when we feed the model with clip sounds, we would expect a higher error score as the model wasn't trained to reconstruct clip sounds. Then we can apply thresholding to determine whether the sample contains clip sound or not. We tested different model architectures such as autoencoders with linear layers, CNN-based vanilla and variational autoencoders, LSTM, which we mimic autoencoders by only comparing corresponding frames between input and output. And finally, we propose our method CNN-AFT architecture, where we process spectrogram on frequency and time axis separately, combining resulting embedding vectors and decode it to reconstruct the input. FT stands for frequency and time. This is our method. It is a CNN-based autoencoder. There are two modules in the encoder part. One processes spectrogram along the time axis dimension, and the other frequency dimension. As an intermediate output, we have two vector embeddings. These embeddings are then repeated along the dimension that was reduced to have the input shader again. They are then combined using weighted sum with learnable weights. We try to just summing, multiplying, or stacking them to two-channel form, but weighted sum work best. Then they are passed to decoder module to reconstruct the input. Since the embeddings have the same shape as the input, decoder doesn't increase the size, just processes using cone layers with appropriate paddings to keep the size. In a way, we hope that utilizing time data and frequency data at a time make the model learn an innate representation of waveform and pure frequency data like output of a Fourier transform, which in turn may help it to learn how to reconstruct it better. Clip sounds on average take approximately 0.1 seconds when constructing the dataset accounting for echo. Sound data were split to 0.4 seconds of sample. Though technically it is only spectrogram is split instead of directly waveform. We use an FFT size of and window size of 512 and a hop length of 256. When converting to the Mel scale, we use 96 frequency bins, which corresponds to the height of the spectrogram in earlier figures. We tried Frobenius distance and Euclidean distance and decided to use the latter since it performs a little better. We used Adam optimizer and trained for 100 epochs, but we report the best results, not last epoch results. As an augmentation, we applied these augmentation methods. Our proposed architecture achieved best results among our experiments. It came from log-mel features. In general, we observed that CNN-based models were performing well, and they achieved best results for the two other features. Though, on average, log-mel features yielded best results. LSTM performed rather poorly, which can be interpreted as this task benefits from spatial processing. As for features, log-mel features and mel features yielded best and worst results respectively. We also found out that in this task that augmentation didn't improve our model's performance. These are our results in ROC-ALP and F1 scores. AUC calculated as the area under the ROC curve, which is the curve of false positive and true positive rates at different thresholds. F1 is the harmonic mean of precision and recall. Overall, models performed on average 0.65 and 0.71 for mass spectrograms, 0.73 and 67 for log-mass spectrogram, and 0.65, I forgot to calculate the other results. Our proposed model yielded 0.75 and 0.73 as AUC and F1 score, which were the highest scores in all our experiments. These are the results for augmentation.
Mr. Sir, your time is finished. Please try to conclude and summarize your work.
Okay, in general, data augmentation didn't improve our performance. To summarize, in this study, we collect clip sounds from real feedback connectors, proposed a novel autoencoder model, and we get 0.75 AUC scores. In the future, we aim to enlarge our dataset and use classification methods. We also plan to optimize our models and integrate them into the smart gloves produced by Motion to enable the employees to do clip sound detection on run time to mitigate failures. That is it for me. If there's any questions, I will gladly answer them.
Okay, thank you very much for your presentation. Dear participants, do you have any questions about this presentation? Okay, I guess there are no questions. We have one last paper, but the authors were not here. I would like to ask once again, are the authors of the paper titled with patch antenna design for Q-band application, are the authors here? Okay, I guess the authors are not here. Thank you very much for your participation to the Congress. I'm ending this session.